Hello, Pre-Algebra. So today is the first lesson we have in our truly flipped classroom. So let's test this out as we start a brand new topic. Topic 3 is all about percents, decimals, and fractions. So we're going to look at how they're related and how to convert between the three different kinds. So we are today going to look at converting rational numbers to fractions. So that will be today's point of emphasis. So you have your note sheet, which is a Freyer model of a vocab graphic organizer. So what you can put on the front side is repeating decimal. That is our term for the first side. And the definition that you can include, or the description, is that a repeating decimal has a decimal expansion that repeats the same non-zero digit or block of digits without ends. And I know this isn't the first time you've seen this, but let's go ahead and look at some examples. So let's take the fraction 2/9. And we want to find out what kind of decimal this is. So as we are studying pre-algebra this year and really getting ready for algebra, we are going to be dealing with fractions a lot because when we represent division in algebra, it's almost always going to be in the form of a fraction. So remember that 2/9 truly means 2 divided by 9. And so for that reason, we can write it out long division style like this. 2 divided by 9. So as we've shown here, 9 will go into not just the 2, but we can see it will go into 20 twice. And 9 times 2 is 18. We subtract and bring down our 0, and we can see the repeating pattern starting to develop. So a few things to remember about repeating decimals is that the dot 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 means that the digits continue without end. So when we see the dot 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 here, we know that's an indication that this pattern of 2, 2, 2 goes on forever without ever ending. So to write that in a simpler way, we will use a repeating bar. So you can see down here that the repeating bar over the 2 means that the 2 repeats without ever ending. So this is 0.2, and the 2 repeats on to infinity. If we look at a different fraction, such as 2/11, then we can remember that 2/11 truly means 2 divided by 11. So we can work that out long division style as we have here. And when we work that out long division, we begin to see a repeating pattern to this fraction. 2/11 really becomes 0.1818, and again we have the dot dot dot, meaning that that 1/8 pattern goes on and on without ends. So in a more specific way, we could write that as 0.18. Notice the bar is over both digits, the 1 and the 8, so it means that it repeats without end. Hopefully that's all review for you. So what we're going to look at now are some examples of repeating and not repeating. So on your Freyer model graphic organizer, you can list some of these examples on your sheet as either examples of repeating decimals or non-examples, ones that do not show that repeating pattern. So take a second to look through some of these, and you might pause the video here while you take a moment to sort out the repeating decimals versus the non-repeating decimals. All right, let's take a second to review which of these decimals are repeating. You might be surprised by some that aren't repeating. So in the repeating column, you could list on your note sheet as examples 0.125 with the bar over all 3 digits. The 125 repeats over and over and over. We have negative 4.1999. That 9 keeps repeating without end because we have the repeating bar over it. Negative 8.46, that 6 repeats forever. And in 0.36, both the 3 and the 6 repeat over and over without ends. But let's look at the non-repeating. 18.35, or 18 and 35 hundredths, is not repeating because there's no repeating bar. 0.2 or 2/10 also has a clear end. It ends in the tenths place. This example is a little trickier because it appears to repeat. We appear to have an 8 that repeats. However, without the repeating bar or the dot dot dot, there's no indication that this goes on. So this would be considered a terminating decimal. And the same with 0.555. Even though that 5-digit repeats 3 times, there's no indication that it continues repeating. There's neither the bar nor the dot dot dot. So these would be examples of non-repeating decimals. So these would be great non-examples to list on your note sheets. So now it's your turn. Take a second to quickly identify whether these would be repeating or non-repeating. And let's just put the examples on your sheet that are repeating decimals. So take a second to identify those. Pause the video. All right, let's check your answer. So of these 3 decimals, the first one is the only example of a repeating decimal. The repeating bar clearly indicates that the 8 and the 5 repeat forever with no end. In decimal 2, we have what appears to be somewhat of a pattern, but not a repeating pattern. We have 40, 4004, and then the decimal ends there. Our third decimal does have the dot dot dot, which indicates that this decimal goes on. However, there's no indication of a repeating pattern. We simply have a 72 dot dot dot. So we know there's more digits to this decimal, but nothing that is repeating because nothing indicates repeating decimal. All right, let's keep plugging away here. Let's take a look at some decimal expansions for some common fractions. And I think you'll begin to notice a pattern. So take a second to grab your calculator and find the decimal equivalents for each of these fractions, remembering that a fraction bar truly means division. So 1/9 would be 1 divided by 9. Think about the way then that you could write the decimal expansion for each of these fractions. So pause the video until you have completed this chart. All right, let's check it out. Hopefully your answers look similar to mine. So we definitely see some patterns with the 9ths and 11ths. Our 9ths, we can take our numerator, and that becomes the digit after the decimal point in a repeating pattern. So 1/9 is 0.1 repeating, 2/9 is 0.2 repeating, 3/9 is 0.3 repeating, and so on. We see a similar pattern with our 11ths. You may have recognized that the digits following the decimal point are multiples of 9. So we have 9, 18, 27, 36, 45. And we continue the pattern from there. So the 0 and the 9 both repeat in 1/11. The 1 and the 8 both repeat in 2/11, and so on. Okay, your turn to write 7/15 as a decimal, and then we will make some observations. As you divided 7 by 15, hopefully you found 0.46, and we put the repeating bar simply over the 6 because that's the only digit that repeats. You may be noticing on your calculator as well that it rounds the final digit to a 7 because it has run out of room to display the decimal going on forever. So that's an indication to you that that pattern continues. But let's look at some decimal expansions below and make a conjecture about the decimal expansions of 3/7 and 6/7. So you'll notice that we have 1/7, 2/7, 4/7, and 5/7 listed. Take a second to analyze the pattern here, and let's see if we can make a conjecture about the decimal expansion for the two missing fractions. So as we look at the patterns here with these decimals, we have a very interesting pattern going on. So to make a conjecture, we are going to kind of take some incomplete information and we are going to propose an idea. So you may have noticed these digits here are the beginning of our digits here. And you may have noticed that these digits here we also recognize from up here. And as we look at the decimal digits of 5/7, we see those exact same digits here in 4/7. So using that information, take a second to jot down what you would conjecture or guess would be the decimal expansion for 3/7. And now using that same idea, let's make a guess about the decimal expansion for 6/7. So as I list the digits for 6/7, I know I am listing the same 6 digits, but just with a different starting spot. So you may have noticed that the digits 1, 4, 2, 8, 5, 7 repeat in every decimal expansion of the sevenths. They just begin in a different place. So if we were to take this pattern, then 2/7 begins with this digit. So we could conjecture or guess that 3/7 would start with this digit, and 4/7 then would begin with the prior digit. So it's kind of interesting to look at some of these decimal expansions and the patterns that come about from these decimals. But let's also take some time to compare mixed numbers and decimals and see how they're similar and how that plays out with decimal expansions. So a mixed number, for example, we know when we say 2 and 1/3 that the 2 indicates the number of wholes that we have. So we have 2 wholes here, and then our fractional component obviously tells us that we have part of another whole. So we have one of the 3 pieces. So in a mixed number, we find our whole number comes before the decimal point, and then the fractional part becomes our decimal. So if we know the fractional parts, we can use that to help us find our digits after the decimal point, and your wholes simply come before. So let's look at an example here that could be used in real life. If a special effects artist uses miniatures to shoot a scene in which a jet flies through a tunnel, let's use our knowledge of mixed numbers and decimal expansions to help us determine if this plane will actually fit through the tunnel. So as we examine this, one thing I want to point out is that this picture appears that the outer diameter of this circle is 8 7/10 inches. However, this measurement down here actually indicates the entire width of the inside of the tunnel. So if the plane will fit through 8 7/10 inches, then it will fit through this tunnel. So don't let that be misleading for you. So we need to determine if 8 7/12 is less than 8 7/10. So let's check it out. So as we divide 7/12 out, we see that